Hi there, welcome back. This is lesson 4 in our nuclear chemistry unit. Today we're going to talk about half-life and how it is calculated. So kind of almost every day so far we've kind of briefly hinted at what half-life is, and today, if you've been sitting at the edge of your seat ever since, well, today is your lucky day and we're going to be going over it. So what works best for today is if you take out or print or look at or something the note sheet that says half-lives of radioactive isotopes. So I'll kind of intro what it is, and then I'll show you how to work through a couple questions, and then you guys will practice. There's also an optional activity you can work on as well, which I'll mention later on. And then tomorrow we will practice more half-life questions as well. So this is the last day of new material. So the way the schedule is working out, today I think is Friday? I'm not sure. Anyway, today we are going over half-life. Tomorrow you are practicing it, or the next lesson day, class that you are practicing it. And then your last day of classes is Tuesday, June 16th. And the last time you have to do is the case study. Now that I'm thinking about it, today is Thursday. Tomorrow is Friday, you're practicing it. And then next week, Monday and Tuesday, you are working on the nuclear chem case study. So what we've done so far and what we're doing today will help you with that. Anyway, this still is the last day of new material. We've made it. As for homework, it doesn't look like anything is due tonight. Just make sure that you are following the calendar and any other announcements your teacher may have. Another thing to stress is that this is the end of the year. Marking period is ending very, very soon, and there's very few assignments left. So you really need to be responsible and take this time to make up any missing assignments, because your window to make up stuff is quickly closing. If you're concerned about your grades or how to make up assignments, please contact your specific chem teacher and talk to them. Okay, enough intro. Let's get into half-lives. So we have talked about transmutation. I'm pretty sure Ms. Vampus and I started the unit off with this word. So transmutation, we're taking an element and turning it into something else. So in natural transmutation, the nucleus spontaneously turns into something else, and we can tell it's spontaneous is because there's only one reactant. It just kind of is very unstable, uncomfortable with itself, so it sheds a nuclear decay particle and becomes a different element. In artificial transmutation, the nucleus of an element needs to be bombarded or collided with another high energy particle. And so this example right there is an alpha particle. And so when the two combined get smashed together, then the nucleus still changes because you had to input and kind of cause that collision between particles that is artificial. So, quick checkpoint question, not on your note sheet, just in the video. A video special question, says which nuclear equation represents a natural transmutation. Take a second, pause it, the video to answer this question. And welcome back to those of you that actually paused and tried this. The answer for this one, as it wasn't already hinted at, because the answer was there, is answer choice for uranium. Because uranium is the only element that is the reactant, and it's turning into something else later on. So in order for something to be spontaneous, there really only should be one reactant. All these other particles were inserted into the equation, and a forced collision was happened to make those other things happen. Okay. Anyway, half-life. If you were to look this up in a textbook, which all of you have, your review book, half-life is the time it takes for half the sample to decay into new elements. So what that means, if I had a sheet of paper and I was ripping it in half, and I told you guys to count. Let's just say it took 5 seconds for me to rip that paper in half. Now, I'm going to crumple up half that paper, throw it out, that's garbage. Now I'm left with half that paper. So the half-life would be that 5 seconds, the time it took for half that sample to decay. Now I'm left with half that sample. I'm going to cut it again. So if I was ripping this paper and I'm asking you to count, it's still going to take 5 seconds. Yes, there is less to work with, but the half-life doesn't, for that specific piece of paper, doesn't change. So another 5 seconds goes by. I crumple up half of it. Now in my hand, I'm holding a quarter of a piece of paper. So now 2 half-lives have gone by. 10 seconds have gone by. I repeat it again. And I can keep cutting it in half, and half, and half, and half, and half, and half again. And when you do that and kind of plot that point, you get an exponential decay kind of curve. Now technically, you're never going to get to be 0, because you always take half of a half of a half of a half of a half, and so on. But for all intents and purposes, once you get to like minuscule amounts, it's practically gone. Okay, so just to kind of go through this picture, the red is your starting material. And so you can kind of see how much of what you started with is left. And so that's the parent isotope. And everything else in gray is the new decay product. So as mentioned before, all the half-lives for these different elements are on table N. So table N tells you the decay particle that's released, but it also tells you what the half-life is. So if we're looking at radon 226, for example, Ra226. Actually, it may not be radon. Radium? Anyway, Ra226. The half-life is 1,600 years. So that means it takes 1,600 years for a sample of Ra226 to decay where only half of it is left. Okay? Now, after 3,200 years, how many half-lives have we gone through? So in 1,600 years, that's 1 half-life. So now this number is just double 1,600, so that's 2 half-lives. So if we start with, one, let's just use fractions, a whole piece of sample. After, in this specific example, 1,600 years go by, now we're left with half. This represents 1 half-life. After another 1,600 years, you're left with a quarter of that original material, and another half-life happened. So now, in total, 2 half-lives have occurred. And so we're going to go over all this in a lot more detail. Now, we kind of mentioned this a while ago, or a couple days ago, common radioisotopes. So if you've taken Earth Science, you've talked about C14, and we're going to spend time on that next week when you work on the case study. So carbon-14 has a half-life of about 5,700 years and is used to date once living organic material. So things like trees and, skeletal remains and stuff like that, things that once used to be living. Now, this is helpful for dating organic material, because if you want to figure out, how old a fossil was, it existed way before your lifetime, and we can kind of look at how much C14 is present. Things like uranium, it has a half-life of 4.5 billion years. Now, that is way more than your lifetime and a bunch of lifetimes. So, if a half-life is really, really long, it doesn't help if, we're dating something that lasts a few years. So things with very, 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 very long half-lives, like 4.5 billion years, those are used to age things like rocks and things that have, been here for kind of since the start of time. And then there are things like iodine-131 and cobalt-60. Both of those have relatively shorter half-lives, one being 8 days, one being 5 years. And these are used in different medical procedures. Iodine is used for thyroid disorders. Cobalt-60 is used for cancer treatments. So with these much shorter lifetimes, half-lives, it decays out of the person's body a lot quicker. Okay, so let's start with this type of question. And there's a few different types of questions the way half-lives are structured. So let's start with fraction remaining. So this question says iodine-131 has a half-life of 8.07 days. A 10-gram sample was allowed to decay for 32 days. What fraction will remain? So our first step is to figure out how many half-lives occurred. So we have 32 days went by, and we can divide that, so this is total time, divided by the half-life length. So how long the half-life is. And that is 8.07 days. And so you can round to the nearest whole number here. So we know 4 half-lives have gone by. Okay? So that is not your answer yet. We have to figure out what fraction remains. So whenever it asks about a fraction, we always start with 1, a whole. Okay? After 1 half-life, half is left. After another half-life, half of a half is now a quarter. So 1 half-life, 2 half-life. Now a third half-life, half of 1/4 is 1/8. And then that's 3 half-lives. We need to get to 4. So half of 1/8 is 1/16. So 1/16 remains of the original sample after 4 half-lives. Now when we're talking about half-life calculations, there is no fancy formula for this. It's just kind of a number line type of thing. And that's it. No fancy complex calculations. Okay. Now another type of question could be, what is the half-life? And so this one says 100 grams of a radioisotope decayed to 12.5 grams after 90.7 years. What is the half-life? So it's giving us where we started and where we ended. And we can use that to figure out how many half-lives occurred. So we're starting with 100 grams. After 1 half-life, we're left with half of that. So half of 100 is 50. Now, we know we need to end at 12.5, so we need to do another half-life. Another half-life goes by, and now half of 50 is 25 grams. Still not where we want to be. And so now half of 25 is 12.5 grams. So now we're ending where we wanted to. And so 1, 2, 3 half-lives have now gone by. Now, in that span of those 3 half-lives, so 1, 2, 3, that was 90.7 years. So it was 90.7 years for all 3 of those half-lives. So there was 3 half-lives in 90.7 years. So what that means is that we want to figure out how long 1 half-life is. So you do 90.7 divided by 3, and you get 30.2 years is 1 half-life. Again, not super complicated equations. It's kind of a number line and cutting things in half. Another type of question is figuring out what the initial amount is. And so this requires a little bit of working backwards, and I'll show you what I mean by that. So this question says, a radioactive isotope has a half-life of 10 days. 1 gram remains after 40 days. What was the initial amount? So we know a half-life is 10 days. And so 40 days went by. If we divide that by the length of the half-life, we get 4 half-lives occurred. Now, instead of given what we're starting with, we're given what we end with. So we're ending with 1 gram. So before it was 1 gram, so here we have to work backwards, and this is what I mean. So we're ending with 1 gram. So before it was 1 gram, it was 2 grams, because we're working backwards. And so that's 1 half-life. If we go backwards again, before it was 2, it was 4. So now this is 2 half-lives that we've gone back. Now before it was 4, it was 8. And that represents 3 half-lives we've gone through. And before it was 8, it was 16. And that is 4 half-lives. So what this tells us is that 16 grams was our starting material. And again, you can kind of work forward and backwards to see what that is. Okay. So if you want, pause this video. There are 4 questions you can practice, as well as 2 Regents questions. You can try them, and if you want to work through them together with me, then obviously keep playing it. And then, of course, you have to have your chemistry meet. I'm pretty sure half of you, if you're watching this, might look like this at times. Okay, so mixed practice number 1. It says, how long will it take for 30 grams of Rn222 to decay to 7.5 grams? So, in this question, your half-life is not given to you, but Rn222 is on table N. So we can look there, and our half-life is 3.823 days. And again, this comes straight from table N. Now, it says you're starting at 30, and you want to eventually get to 7.5 grams. So, we have to figure out how many half-lives occurred. So half of 30 is 15, and so that is 1 half-life. But we want to end up at 7.5, so we're not there yet. After another half-life, so half of 15 is 7.5, and so now that's 2 half-lives. So we know that 2 half-lives occur, and 1 half-life equals 3.823 days. So how long is 2 half-lives? All you have to do now is do 2 times 3.823, and that gives you 7.646 days. That's it. Okay. The next one says how many grams of nitrogen-16 will be left from a 16-gram sample after 21.6 seconds. So, what you have to do, this specific element has a very, 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 very short half-life. And it says over the span of this time. So we have to figure out what the half-life is. So this number tells you how much time went by, but is not the half-life. If we look at table N, the half-life is 7.13 seconds. Incredibly, incredibly short. So it's saying, okay, if a half-life is 7 seconds and it goes on for 21 seconds, how much is left? So the first thing we want to do is figure out how many half-lives that went by. So you take the total time and divide that by how long the half-life is. And that means 3 half-lives occurred. So it wants you to figure out how much is left. So if we start at 16, after 1 half-life, half of 16 is 8. Again, that's 1 half-life. After another half-life, we get half of 8 is 4. That's 2 half-lives. After another 1/2 of 4 is 2. And that's 3 half-lives. So 2 grams are left. Okay. Next says how many half-lives will it take for 50 grams of TC99 to decay into 6.25 grams. So this asks for the number of half-lives. So it gives us our starting material and wants to know how many half-lives it will take to get to 6.25. So half of 50 is 25. We're not where we need to be yet. Another half-life. Half of 25 is 12.5. Not there yet, almost. Half of 12.5 is 6.25. So we know 1 half-life happened, 2 half-lives happened, 3 half-lives happened. So the answer is 3 half-lives. Okay. Last short answer question, kind of. It says, what fraction of a sample of phosphorus 32 will be left after 42.9 days? So the half-life, according to table N, is 14.28 days. And so we know 42.9 days occurred overall. Divide that by the length of 1 half-life. That means 3 half-lives have occurred. So if we're talking about fractions, we will always want to start off with a whole. So that's 1. After 1 half-life, we're left with half. After 2 half-lives, half of a half is a quarter. After 3 half-lives, a half of a quarter is an eighth. So you have 1, 2, 3 half-lives. So 1/8 remains. Lastly, there are 2 Regents questions, and I'll go through them pretty quickly. Number 1, you have to look at table N. So I did have this on the website a little bit clearer. It asks you which has the same decay mode and half-lives greater than an hour. So AU, we should start with A, has a half-life of 2.9695 days and is beta minus. Its pair of N, 16, has a half-life of 7.13 seconds and is beta minus. So they have matching decay modes, but this is not more than an hour. It can't be A. B, iodine 131, is the half-life is 8.021 days and it's beta minus. And P32 has a half-life of 14 days and is beta minus. So both of these are more than an hour and they have the same decay mode. Just because I'm running out of room and it's going to get really messy, I'll just explain C and D. For C, calcium 37 has a half-life of 2.13 times 10 to the 5 years and beta minus decay. Fe53 has a half-life of 1.592 times 10 to the 5th years, both of which are way over an hour, but the decay mode of Fe53 is alpha, which is not the same as beta minus. And D, they both have half-lives way over an hour, both of them have it times 10 to the 5 years, but the half-lives are different. One is beta minus, one is alpha. So the answer has to be B. Okay. Lastly, number 2, for the Regents questions, it says, after decaying for 48 hours, 1/16 of the original mass of a radioisotope remains unchanged. What's the half-life? So, we're given how much is left. We have to figure out how many half-lives went by, and then how long each half-life is. So, for starting with fractions, again, you always start with a whole. And after 1 half-life, half is left. After 2 half-lives, a quarter is left. After 3 half-lives, an eighth is left. After 4 half-lives, a 16th is left. So 1 half-life, 2 half-life, 3 half-life, 4 half-lives. So, over this time, this is 48 hours. So 48 hours equals 4 half-lives. So how long is 1 half-life? You do 48 divided by 12 equals 48. So the total amount of time divided by the number of half-lives, 4, is 12 hours. So that means each half-life is 12 hours. So 12 hours to get to a half, another 12, and another 12, and another 12. Boom, that gives you 48 hours. Now, this is it for today. I do want to mention this optional activity should you want to try it. So the second sheet of this kind of note sheet in the document says the half-life of a Twizzler. In class, we would have actually played with Twizzlers and you could have eaten them, but whatever. If you have a Twizzler at home or any other object you can kind of rip in half, you can try this. So there is a graph on the bottom of that second sheet, and this kind of walks you through what you need to do. So whatever you're using, you will need 2 of. You place the first one on, half-life 0. So your y-axis, you're just going to label amount, and then your x-axis will be number of half-lives. And so lay down the first object, just mark on your page where it is. And then for that second one, cut it in half and place it on half-life 1. And then you can cut in half again and again and again. Each time when you mark how tall your object is, and you can kind of create that graph to get that decay curve. If you do this and want to send a picture of your candy graph, whatever object you're doing, to your teacher, I'm sure they would appreciate that. And then on the back of the sheet there is some more half-life questions. If you want answers to them, you can email me. That is fine. Even if you're not my teacher, even if I'm not your teacher, if you want answers to these, I can share these with your teacher, but you can also just email me and save that extra step. So that's it. Tomorrow we will practice more on half-lives. On that note, have a wonderful day.